Okay, so this is going to be our introduction to circles. Yes, we've skipped some chapters, but in order to address those chapters accurately, we need to talk about these first. Okay, so we're going to talk about area and volume and stuff like that in chapters, I think it's 10 and 11, which we're going to talk about volume and area, surface area of like cones and cylinders, and components of cones and cylinders or circles. Okay. This is one of the topics that I want to make sure that we fully cover before the end of course exam because it's probably somewhat completely new to you. Okay, but it is the introduction to circles, and what this chapter is about is taking certain lines and segments and intersecting them with circles and developing relationships that always exist. Okay, and what we're going to find out is that there's a lot of links between circles, lines that intersect them, and triangles that we have already talked about. Okay, we see the word tangents. We've seen it before. We've seen tangent as opposite divided by adjacent. Right? Okay, when we talk about SOHCAHTOA, there's a direct link between why that ratio uses the same word as what we're talking about today. Today we're going to be talking about a shape, a certain segment or line that we refer to or call as a tangent line. Okay. The first thing I think is important for you to maybe write down is what a circle is. Okay. Kind of give you a visual image here. I'm going to take point A and point B. I'm going to take A and I'm going to make it static, meaning that I can't move it. So I'm going to make it red. I'm not going to move A, but I'm going to move B. But I'm going to move B so that it is always the length of F away from A, meaning F is that distance, 4.05. So I'm going to move B so that it's always 4. That was terrible. How do I do this? I'll do it this way. All right, so we're going to move B, so in this case, it's always a distance of 4 away from A. Okay, so if I put it there, it's 4 from A, right? If I put it there, it's 4 from A. If I put it over here, it's 4 from A. Okay, and I'm going to highlight all those different points that are 4 units from A. And what do we trace out? A circle. So each one of those blue dots is a point that is 4 units away from A. Okay, so that develops a circle, and that's how we define then a circle. Okay, the definition of a circle is the set of all points that are the same distance from a given point. Okay, the set of all points that are the same distance from a given point. Sometimes instead of using the word same distance for the phrase, we use the word equidistant. Okay? So saying it that way, it's the set of all points that are equidistant from a given point. Okay? Set of all points equidistant from a given point. Okay. Now, every once in a while, because it's giving you varying versions of this definition, some texts will refer to the set of all points. And anytime that we ever use that phrase, a set of all points, I guess set of all is analogous to the word locus. We say it's the locus of points equidistant from a given point. The given point, A, would be the what of that circle? Where's it at in the circle? Center. Okay, so that's A, is the given point is your center. Okay, but I think it's now this This PowerPoint doesn't introduce or write out that definition. When I wrote this PowerPoint for a different textbook, and we already talked about some circle stuff prior to that, I just haven't updated with the new text yet. But in the things that we do, it's going to be beneficial to have that definition of what a circle is, okay, and think about it that way. All right, so everybody okay with that? What is that length AB then? What do we call that for a circle? It's the radius, okay? And that is the only distance, that is the only measurement that defines a circle, which is really nice. Because a lot of, like if I have a rectangle, that is defined by a length and a width, right? Okay? So a lot of the shapes that we deal with are defined by multiple things. Triangles are defined by multiple segments and multiple angles. A circle is defined by a singular value, the radius, which is really nice for a lot of things that we want to do. All right. Now we want to talk about what a particular type of line is referred to as for a circle. Because if I take there's just point B, okay, would you agree with me that there is a point, not a point, that there is a line that would go through B, no matter where B is? Okay. In that line, let's just construct it here using GeoGebra's tools. Would you agree that that red line always passes through B? Okay. Now, B is the only point that we have on the circle, right? It's the only point that we have defined on the circle. So how many times does that red line pass through our circle? If I zoom in, okay, I'm just going to zoom in like right here, but this can happen everywhere. Is the red line in the circle, are they different there? Okay, so let me see if I can kind of pull down here and get closer to B. Just because I'm zoomed in so far, sometimes it wants to disappear on me, so let me get back to standard view. If I zoom in as much as I can on B, there should always be, and you can start to kind of hate that. I'm not going to do it anymore. But you can kind of view that as closer and closer I get to B, there's always going to be a gap between the red line and the black curve, right? Or the red line and the black circle. Except for when I get right on top of B, they're going to be shared. Does that make sense? Okay. So this red line, and I can move it around as I move B, that red line is intersecting my circle one and only one time. And that red line is referred to as a tangent line. Okay? So I'll write that definition up here for us. It says a tangent to a circle. Now, it's important that we say to a circle because we can be tangent to other things. We can be tangent to parabolas. We can be tangent to other smooth curves in the XY plane. Okay? Right now, we're just talking about circles. Okay? Being tangent to circles. But this is kind of the introductory to one of the main components of calculus and what allows us to do a lot of the calculus that we do. Okay? But it says a tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. A lot of important phrases up there. Maybe the number one phrase that's important here is that it's in the plane of the circle. Okay, that's all that means here in a moment. The next important phrase is that it says exactly one point. Can't be 2 points. Can't intersect your circle two times. Can't be 3 times. Can't be 0 times. It has to be exactly one time. Okay. Where if we do that word exactly, we've seen this over and over in this course. We say, and then it's a line in the plane of the circle that intersects the circle in one point. Then that opens the door of saying that it could be 2 points because 2 points is at least 1 point, right? Okay. That is not a tangent line when that happens. So we should be careful with that. Okay. So any version, or sorry, any portion of that red line, whether it be a segment or a reg, is going to be referred to as a tangent of the circle. Okay. The point in which that line touches your circle, the point in which that line touches your circle is referred to as your point of tangency. So point B here in this image is our point of tangency. All right. So I want to go back to GeoGebra and just kind of mess around with this a little bit. Because this is always a fact that people struggle with. A lot of times in the problems that they give us, or the problems that we see, we might not necessarily have that line. We might have a portion of that line. Well, that portion of that line is still tangent to the circle. Does that make sense? Okay. And I could do this. I can make it that portion of the line. Okay. It's still touching at that point right there, B. And I still have a tangent. We call that a tangent segment. This would also be a tangent segment, okay? A lot of times we're actually going to deal with just that one, though, from C to D, okay? Or B, whatever point you want to call it. However, is that a tangent segment anymore? Is that touching my circle? No, okay? The extension of it is, so if I extended beyond where D currently is, put back in that line, that line is tangent, but that little segment is not. We can also, look at, maybe do it this way. That ray is referred to as a tangent ray. Is that okay? And it can go in both directions. It doesn't have to, have to start at C and go that way forever. And we have our tangent ray that way. All right. So any portion of a line, as long as that line is touching your circle one spot at one time, and then any portion of that line is touching your circle at one spot is referred to as a tangent. Okay. Doable? All right. That brings in this first theorem here, okay, and we're actually going to talk about this theorem and its converse because they are both, in fact, true. But it says if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. If a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. Another way of saying that is that a radius and a tangent line are always perpendicular at the point of tangency. Okay? And I'll come back and let you write that down, but just to prove this to us using GeoGebra, okay? The black segment's our radius, right? The red one is our tangent line, okay? No matter where I move B, is that always a 90-degree angle? Yeah, okay? And that's a huge concept for calculus and a huge concept for physics. Think about, you guys know what like an old-time slingshot looks like? Okay. No. Like a Bible slingshot. All right, so like it's just a piece of leather, like a leather cord, and then in the middle of it is a little pouch, right? And you put a rock in that pouch, and you take that end and that end, and you put them in the same hand, and you start rotating this thing around your head in a circle. Does that make sense? Okay. Some of you do this with, like, anybody got, Gage, give me your lanyard. So a lot of you guys do like this stuff, right?
I do.
Okay. Well, when I let go, you got anything here you can break? So if I let go, does anybody know what path the keys are going to take when I let go?
This way.
Well, it depends on where I let go. If I let go down here, when the keys are down here, it's going to go that way. If I let go here, the keys are going to go that way, right? If I let go here, the keys are going to go that way. Where is it going to go?
Where the heavier and heavier.
Think about my keys. My keys and that description, or my my rock and my slingshot. If you had a bird's eye view, it would be that point B, right? Those are the keys, or the rock. And when I let go right there, okay, so it was rotating this direction, right? When I let go, where's the rock or key is going to go? It's going to follow the path of that tangent line. Okay, does that make sense? Okay. Okay. Finally, 4 weeks of baseball, and he finally caught his first object. That's awesome. All right, so in physics, in other courses, and a lot of science stuff, and a lot of like engineering, we're interested in that tangent line. Okay, let's say that I have maybe a road, and we're looking down on this road, and it's of that form. Okay, and let's say we've got icy conditions, so we eliminate friction. Okay, and I'm traveling on this road, and I lose control right here. Where is my car going to go? Okay, well, my car should take, so I lose control at point A, and I want to know, where does my car end up? My car should end up following that black tangent line. Okay, does that make sense to everybody? But if A, maybe I lost A right there, it takes another path, correct? It takes another path depending on where A is. All right, and this is calculus, and this is how maybe like investigating wrecks and stuff like that, and how we can determine how fast somebody was going, or we can determine maybe conditions, that kind of stuff, and forces and all that kind of stuff, all the interesting stuff that we do in a physics class, or a forensics kind of analysis of a wreck. We can use geometry and calculus to determine a lot of important variables. Okay. One of the main components of calculus is finding slopes. Okay. My interest is, you guys know, if I look at that line, the slope of that line is always negative 0.53, no matter where, right? Okay. But if I look at this curve here, the slope on that curve is different everywhere. Okay. There are a couple spots that are the same, but it's because this curve repeats itself over and over again, is why they're the same some spots. The way we determine the slope of these curves is we actually look at the slope of the tangent line of those curves. Okay. And the slope of those tangent lines, let's say I want to know the slope at x being a little bit bigger than 1, the slope is going to be 1/3 of that red curve, or sorry, green curve. Does that make sense? So what I'm trying to do here is just, and there's a lot of math in between now and then, but trying to open your eyes to the fact that when you get to calculus, it's a collection of the previous 4 or 5 years. Okay? And you use a lot of those facts, and this is one of the main facts that we use to really start investigating and learning calculus, and being able to use that calculus to really benefit us in understanding how the world works. Okay. So one of our key features here is that our radius is always going to be perpendicular to that line that is tangent to our circle. Okay. Now let's talk about why they call it a tangent. Let's take, and it doesn't have to be this segment. It could be a line that connects that segment. Okay. Meaning that it could be, or contains that segment. It could be that line right there, but it gets kind of messy the more lines I put in here. So let's just deal with the segment. But if I look at that segment there, or that line, is a what for my circle if it passes through the center of my circle? Diameter. Okay, it's a diameter. So the inside portion is referred to as the diameter. Okay. Now the entire line is actually referred to as a secant. All things that we'll talk about later on in this chapter. But if I look at just a portion of that diameter, or that, I guess, secant line, what do you create right there? A triangle. What kind of triangle is it? A right triangle. So what are you allowed to use in every right triangle to find side lengths or angle measurements? SOHCAHTOA, right? Okay. If you said Pythagorean theorem, you're right. All right, but I'm going to, would you guys agree that that blue segment right there is a part of our tangent line? Okay. And if I just hide the tangent line, that blue segment is a tangent segment, right? Okay. I'm going to make my circle have a radius of 1, I think. Just makes things a little bit easier. Doesn't really matter, though. Where's that segment that I decided to be? There we go. Maybe I can't change it. All right, it don't matter. If I look at that distance right there, which is the blue distance, and then I look at that red distance, okay, and I focus on that angle right there, this blue distance would be the opposite, and this would be the adjacent, right? Okay. Now that blue distance is 5.99. That red distance is 4, right? I'm going to take K divided by F, which is this 5.99 divided by that 4, which are these two segments divided in that order, and it gives me that number 1.5. Okay. Now there is also an angle here at A, right? 56.28. I'm going to take and see what the tangent of that angle, 56.28, is. What do you recognize about those two numbers? They're the same, right? And that's why this is referred to as a tangent line, because it encapsulates the tangent of this angle being the opposite of that divided by the adjacent, or the opposite of this angle divided by the adjacent of that angle. Okay, and that's going to be the same no matter, those two numbers E and L down here are always the same no matter where I move D, no matter where I move, B. I'm always going to have that right triangle, correct? Okay, and no matter, like I said, when I move D, it changes that angle measurement, but I still get that ratio to equate. Okay. There are also links. I'm not going to show them right now, but and this is what we do in trigonometry. There are links between that circle and sine and cosine as well. Okay. And tangent, cotangent, secant, and cosecant. But every time that I have a line of tangency, or a tangent line, and a point of tangency, I'm going to have a right angle here. So this triangle is always a right triangle, correct? So you can always deal with SOHCAHTOA, you can always deal with the Pythagorean theorem, and all that kind of stuff as we kind of investigate these circles and triangles. All right. The converse is that if let's get back to this. Let's say I know nothing about that red line, but I do know that it's perpendicular to the black one at this point. What's that telling me I know this red line to be? What could I classify it as? The last theorem said that if a line is tangent to the circle, then you get the tangent line and the radius to be perpendicular, right? Now what I'm saying is all I know is that this line here, or that segment and that segment, are perpendicular. I know this is a radius. I don't know anything about the red line, but if they're perpendicular, what can you classify the red line as? A tangent line, okay? And that's ultimately the converse of this theorem here, which I've got written down here towards the end It says if a line in the plane of a circle is perpendicular to the radius, at the end point of the radius, that's key, okay, it has to be at the end point of the radius, then that line is a tangent line. Okay, so I'll let you write that down. And while you're writing that down, I'm going to do something else real quick for us. All right. There's a. We're okay. We need more time on that. Need more time. Yes. Does everybody have this one written down? All right. The other one was there. And that's, looking at these two things and maybe wanting to write both these down is, if you remember back to like chapter 2, the reason why we spent so much time on chapter 2 and trying to understand like if-then statements and converses is when you're in a math class, maybe at the next level in a college math class or something like that, the professor might just say, here's a theorem, write it down, we talk about it, but then they might end and say, okay, converse is true as well. And then they never deal with it, never talk about it, okay? But you know what a converse is, it flips the if and then, so now you can on your own kind of maybe in your notes add that in when you need to, okay? But like our textbook, like we said in chapter 2, is always going to be written, if the converse is indeed true, they will write it as separate, distinct theorems, and then it's kind of our task to recognize that they are indeed converse or not, just flipping the if and then parts. So in both of these theorems, whether the initial one, 12.1, or its converse, a key phrase here is in the plane or in the same plane. And that gets us to thinking about something like this, okay? A three-dimensional rendering of what we've been dealing with in regards to our circle and our tangent line. That is this line here. I don't know if I can color it in 3 dimensions. Yeah, for some reason that won't color. But if I look at that line, it is still referred to as tangent to our circle because it is in the same plane as our circle. Our plane, would you agree that our circle is in, is that blue plane? That kind of makes sense? Is the line in that same blue plane? Okay. Here's where we kind of get issues. Well, bear with me. All right, so we've got that plane. Would you guys agree that, I'm going to move F around a little bit, that the line there, that red line, would you agree that that intersects my circle at one spot there at E? Okay. And let's just make it a little bit more kind of dramatic. It's kind of a pain in the butt. There we go. A little bit more dramatic. Still not great, though. I don't deal with the 3 dimensions enough to get a good grasp on it. Let's do that. All right, that's better. Would you agree that that red line intersects my circle one time? Is that red line in the kind of teal or turquoise plane? No. So even though that red line intersects my circle once, that red line does not meet the full requirements of being a tangent line. Does that make sense? So just saying it's a line that intersects my circle once is not enough. It has to be a line that's in the same plane, or it has to be a line that is coplanar with my circle. Okay? So just keep those things in mind as we're answering questions. Maybe some like always, sometimes never questions or true and false questions based on that vocabulary word. Just got to pay attention to that. Here are some questions that you're going to see that are, based off of that idea that your tangent lines and your radii are perpendicular. What kind of angle do you have? If this is a radius and LM is a tangent line, what kind of angle is L? Right angle. Same thing down here at N. What kind of angle is that? Right angle. Okay. So how many degrees would you have for that figure there? 360. So to find x, don't I take 360 minus the things I know? So minus 90 plus 90 plus 117, and that should give me x. Is that all right? Is that pretty easy? Okay. So they're using the fact about tangent lines to help us kind of work our way back into other areas that we've talked about in the past. Another version or style of question that you're going to see is something that looks like this. They're going to ask, is ML a tangent line? Is ML a tangent line? Well, if ML was a tangent line, what kind of angle would you have here at L? A 90 degree. How do I check to see if it's 90 degrees? What theorem have we always used to check 90 degrees? Pythagorean theorem. So I could say, now you got to be careful. You got to know which one's the hypotenuse. What number up there would be the hypotenuse if that's a right angle? 25. So I take 7 squared plus 24 squared and see if that gives me 25 squared. 7 squared is 49. 24 squared? 576. 25 squared? Come on, nobody knows 25 squared? That's a common one. 625. Is that a true statement? Yeah. Take one of those away and put it into there. 50 plus 575 is 625, right? Okay. So that's a true statement. So is that a right angle? Yes, it is. Okay, so that's a tangent line, right? You're going to see questions like this. This one's kind of more difficult because there's a couple things that people don't really recognize here, and you do see a series of these in your homework. I want to know what is the length of essentially BC, right? Well, what kind of figure is this? What kind of triangle do we have? It's a right triangle, isn't it? What is one of your legs for that right triangle? Is that a leg? Is that a leg? So 12 squared should be 144, right? What is your hypotenuse? X plus 8. And then because of the Pythagorean theorem, we're going to actually square that, right? The one thing I see a lot is that people want to write 8x. Make sure we're adding here, okay? And then the next error is an algebraic error because we want to go x squared plus 144 is equal to what? What does this become? So a lot of people write x squared plus 64, but you missed something. Because doesn't x plus 8 squared mean this? So what am I missing there? I'm missing my 16x. I'm missing O and I, right? That is a very, very common thing for an ACT to do to you and the end of course exam to do to you because they know a lot of people want to just take x and square it, 8 and square it. You have to know that that's foiling and you got that 16x. So now what happens with your x squareds? Drop out. I got 144 now. It's a two-step equation. And x ends up being 5. Okay. Later on, the question will be, what's the area of that circle? Okay, they'll start you off with this picture and say, what's the area? And we should be able to do that once we talk about what the area formula for a circle is. Anybody know already? Say again? That's the circumference. So that might be a question to ask. What's the circumference? Area is pi r squared. So the area of that circle would be 25 pi. Let's see here. All right. This says if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. Okay. Walking you through that. This is very, very simple. Okay. If I have a circle, okay, and I have two tangents to that circle, and they share an external point. So that external point is C. So I'm going to draw every external point. I should be able to draw two tangents to the circle. Those are the two tangents. Okay? Now we are interested in not the whole thing. We're just interested up until point D and E. So let me take that distance there and that distance there. So what they're saying in that last theorem is those blue dotted lines, no matter where C is, it's on the outside, those blue dotted lines are the same length. And if we look down here, it's showing you those same lengths, right? But I want to talk about why. If we take that distance and that distance, what's the relationship that you know about those two distances? They're equal, right? They're both radii of the same circle. So congruent, right? What do you know about this angle here and that angle there? Right angles, correct? And they should be congruent. What do you know about that green segment? Oh, it's a terrible color. That segment. Is it congruent to itself? Okay. If I look at this top triangle, it's a right triangle, right? Is that a leg? Is J a leg? Is K a leg in the bottom? What's this dotted line for both? What's that purple dotted line for both of them? It's the hypotenuse of both triangles, isn't it? Are those two triangles congruent by hypotenuse leg? So then why would these blue lines be congruent? Careful. We've already, because you're saying side, side, side or something like that, we've already used hypotenuse leg to prove the triangles are congruent, which would be what side, side, side or side angle side would do for us with non-right triangles. But those blue lines should be congruent by CP, CTC, right? Okay. So when they tell you that those, in that theorem, that those two segments are always the same, no matter where C is, as long as C is on the outside, because if C is on the circle, the tangent lines disappear, right? Or if C is on the inside circle, the tangent lines disappear. But no matter where those are, you always get those two triangles that are congruent to one another. Okay. And then by CP, CTC, then we have these external these tangent lines being congruent. Does anybody know what this quadrilateral here is? Say it again. It's a kite. Okay. Everyone, we might be able to get down to a situation where, I don't know, I have to think about it. Wonder if we can make that distance there the same as that one to where it becomes a rhombus. I'm not sure we can. Maybe we can. I don't know. But in general, that's a kite. There's a couple other things, guys, I want you to kind of work through in addition to tonight's homework. These last handful of slides, we've already talked about slide 12, okay? But slide 13, 14, 15, and 16 give you some vocabulary words that are going to help you inside tonight's homework. They're really easy. If you read them, see the pictures, you should be able to develop an understanding and perform pretty quickly. We will also talk about them at the beginning of class tomorrow. You may go to lunch.